It's 2:02, so I think we can get started. So hello everyone, welcome to ethics seminar series. I'm John, a seminar coordinator, and together with me is Miss Kathy Medley. Kathy and I will be today's moderator. And our director, Ann Williams, and associate director, Rob Ferrero, and our assistant director, Andy, also join us. And Ralph will be introducing the speaker before he gets started. And just so you know, this seminar is being recorded, and the video will be published on our YouTube channel. So please feel free to check it out. It usually takes a couple of days. Before we get started, I will have our Associate Director, Ralph Ferrero, to introduce the speaker. So Ralph, please go ahead.
Yeah, thanks, John. Yeah, it's a pleasure to have Professor Witold Krajewski, University of Iowa, to give this talk about predicting stream flow. Some of you may have heard, Andy and I have a long history with him going back many years ago when the satellite precipitation work really was just getting off the ground, and Vitek and his team have been throughout that last 30 years or so been just very prominent in the field. And so it's just a pleasure. It's great to see him again. He's ageless. He looks the same all the time, always full of energy, and look forward to his talk coming up. So Vitek, will turn it over to you.
Okay. Well, thank you very much. Thank you, John, for the invitation. I would like to say that I lived in Maryland for many years before moving to Iowa. So there is this professional connection, but also more, physical connection. So it is great to be back in Maryland virtually, So, but let me start sharing the screen now, and so for today, I promised in my title to talk about hydrometeorological challenges of streamflow forecasting. And but I have to start my talk by talking about the Iowa Flood Center. And this is for several reasons. One of them is that this is something very unique at the scale of the country. Iowa Flood Center was established by the state legislature. I'll show you in a moment. But also I wanted to gain some credibility with you that I know a little bit about streamflow forecasting. And so, so here it comes. The motivation for establishing the Iowa Flood Center was this big flood of 2008. So this is city of Cedar Rapids, about 30 miles north from Iowa City, where the University of Iowa is located. So just a tremendous, disaster, as you can, see. Of course, we do see similar photos from all over the country, from all over, the world, but this was a big one here in Iowa. And the legislators and the leaders of the state at that time, they recognized the potential that we had at the University of Iowa to help, and they established the center and put us to work. And so here I just highlighted the key words here from the bill that established the center. Then different day, the university leaders appointed me as director of the Iowa Flood Center, and then we went to work. And so to address the need for better monitoring of streams and rivers, we conceived and designed and prototyped and built and tested and now have operated almost 300 of these bridge sensors. So they measure the distance from the bridge to the water, table. They are autonomous, so equipped with battery, which is charged with solar, panels, and provide, data in near real time, so every 15 minutes or so. And so this is the network. You can recognize the color coding. USGS in green, Iowa Flat Center in blue, and the red are desired, requested, locations. So we can see that we have a pretty nice, network here in the state of Iowa. These things, they do work. So this is one in action, a flood, and you can see the center in the center of the slide. And when you put them, together, collocated with USGS gauges, then it's hard to distinguish one from the other. So you see one line, but there are actually two lines, here on this, plot. So they definitely, work. There is one of them in action. So this is from a flash flood in Des Moines, in the center of the state, 2018, summer, and you can see how quickly the stage, how quickly the water rose, and then there was the bridge. That particular sensor was submerged, so there was no communication. And when the water level went down, the communication resumed automatically without us doing anything. So so people like those sensors. They like to look at them. And that's why this high demand for the technology from us. Another thing that we have done for the state, we have developed inundation maps, both for communities, large communities. So this again, the flood extent that corresponds to that photo that I was showing you before. So, but it's not a historical drawing. This is just how far the flood could extend. And so we have developed, these maps with detailed models of open channel flow, so that mimic how water flows in streams and rivers. We have also developed approximate, maps everywhere, even for small, streams. So again, they can be related to the probability of exceedance, but we often talk about those maps and the extent that you see as a potential. So this is not necessarily for forecasting, but it shows the potential of what could happen. So that was another big development. Took about 6 years. And then what is most relevant to my talk, today is that the Iowa Flood Center has developed a real-time streamflow forecasting system. And of course, a system like that has to have a model, and our model has the resolution of what I will call a hillslope. And you can see, actually what you see is not a photograph. This is an image constructed from LiDAR topography data. And so you can see the resolution, you can see the roads, and you can see also a construction of our model, this irregular polygons, which are hill slopes, and that's the fabric for our model. The model, of course, is driven by rainfall, so I'll come back to this. And then the hill slopes on the left here are responsible for converting rainfall into runoff. And so there is a set of equations that address that conversion and water infiltration into the soil, and then percolating, deeper. Also evapotranspiration from the surface and subsurface, and the runoff generation. And each hill slope is connected to a link, a segment of a channel, and these links then form the drainage network, the river network. And so again, once the water is in the channel, then it is routed through that network across the scales, from the scale of a hill slope, which is a fraction of a square kilometer, all the way to large basins. So here in Iowa, about 30,000 square kilometers. And all these equations are ordinary differential equations, but there are many of them, and they need to be solved, quickly. And we have clever algorithms to solve, the system, so we can update our forecast. In principle, every 15 minutes, we actually do it, once an hour. And the forecast then is everywhere, because the hill slopes are everywhere, the streams are everywhere. So this is what we do. So this system then allows to make this kind of forecast of the potential of flooding, because notice that at most locations, and so here locations are small communities, and here in Iowa we have about 1,000 small communities that are located by streams and rivers. So most of them, great majority of them, they don't have any gauges. So the forecasting system would give these people the amount of water that is expected to flow at such and such time. They wouldn't know what to do with it, because they have no way of relating, to that. So we have developed an index, we call it flood potential index, and then we can color, the map. And also we can index how things would be progressing, through time in the near future. And so that way, people get the information. So essentially, when things are within the channel, then you get different shades of blue. So there is nothing, to be concerned about. When things, get into yellow, orange, and so on, then people should start, watching, the weather, and watching the situation, take care of their possessions, and so forth. So again, this system works in real time, everywhere. So well, so this was, that background. So I hope that I established some level of credibility in terms of stream flow forecasting. You may ask, a question, well, what about the National Weather Service? Why are you doing, this? And I would say, no, we always give the priority to the National Weather Service. But the fact is that as we speak, today, they do not have the same kind of, capabilities. And so the National Water Center in Tuscaloosa, Alabama, yes, they are working on this. They have some prototype, models, and we are working, with them, but they don't have the same, capabilities. So we have this gentleman's, agreement that whenever and wherever they issue a streamflow, forecast, we don't show our forecast. But when they don't, or where they don't, well, then, it's an open season, right? If you can, you do it, so we can. All right, so now what about those hydrometeorological, challenges? So I'll start with the hydro, part. And actually, I will not say too much about it, because this perhaps to a different, audience. I have something left, for you. So the issues are, of course, how to convert rainfall into runoff, and that requires knowledge of the attributes of hill slopes, so size, slope, land use, soil properties, and so forth, as well as those, channel, links. So again, land, slope, roughness, geometry, and so on. So we know some of those, parameters, but still, even at the scale of a hill slope, there is tremendous, variability. And of course, for very small, streams with changing seasonal, vegetation and, sediment transport and all sorts of other, issues, we cannot be precise, all the time. So of course, all this introduces uncertainty into our model. So yes, there is hydrologic model and uncertainty. So so that's about that. So then meteorological challenges. So I will say a little bit more about this. So you heard from Ralph that I have some expertise on the topic of especially QPE. So here it comes. Let's say that so this slide will kind of establish the framework a little bit, just to make sure that we are all on the same page. So let's say that this the QPE, and that QPE may translate into this kind of response at some location, arbitrary location in the stream network. Now, if we know, so we are at this point in time that I call now, and now somebody can give us a QPF, quantitative precipitation, forecast, and if that forecast is good, well, then it may actually lead to quite a different shape of the hydrologic response. So I organized my talk into those two elements. I will not talk too much about how to construct the QPE, and I will instead give you some insights, more like hydrologic insights, how all this play, because I already acknowledge that there is uncertainty associated with the hydrologic model, and now I will acknowledge that there is also uncertainty associated with the QPE, and we will get to the QPF. Okay, so well, basic issues, right? So one issue is what should be the resolution, and of course the immediate answer is like the highest the better, so as high as you can provide. Well, okay, well, so we'll see, and of course about accuracy, as accurate as you can provide, right? So those are the answers. Well, let's take a look at this simulation experiment. So here the reference is 1 kilometer resolution of the QPE, and then you could see that with our model we could observe, we could estimate flow everywhere. So at very small streams, and then bigger streams, and small rivers, and large rivers. So here in this simulation, we monitored the peak flows at all these locations. And of course, for the small, for the hill slope and small streams, there are many, well, millions over Iowa. And then as the scale increases, there are fewer and fewer of those. Well, so as I was talking, I hope you could explore this plot, and you can see that as the resolution, and this is in space, increases, well, then of course the variability and therefore uncertainty increases also. But you can also see that as the scale of the basin increases, the variability reduces, drastically. So for example, at the scale of say 100 square kilometers, whether I use 1 kilometer or 2 kilometer resolution, it doesn't matter, anymore. And certainly it doesn't matter when I go to 1,000 or 10,000, square kilometers. So which is, Ralph, good news for the satellites, right? Because, the resolution is not as good. And here I'm showing that for certain, size basins, actually, we wouldn't be, hurt, too much by this lower resolution. Well, so that was like one insight. I will say, I'll go back here. I do not have a slide here to show you what happens in time. In time, we wouldn't have a symmetry. We would have a systematic bias in such results if we go from, say, high resolution in time, I'll just call it, hourly, let's say, to daily. So, and that bias is because if you have to wait a day before you even start your forecasting, then immediately you would be delayed. And that, of course, would introduce a bias. That bias also disappears as the scale increases, because then the overall travel time in a large basin is, a large multiplier of that time that I lost waiting for my data, right? So if it takes 2 weeks and I just wasted a day, well, then perhaps the penalty is not that high. Well, so moving on, this is another view that brings that hydrologic, perspective into the picture, and that is that you have a river network here, and now you have all these white points, and the characteristic of these white points is that they are equal travel time from the outlet. So here, I hope you can see my cursor. The outlet is at Cedar Rapids, and all these points are distributed, through the basin. But again, same travel time from the outlet. So let's say I'm making my radar-based estimate, and the true rainfall is the green, and I'm making an overestimation, error, which is in red. So that happens in this point. And then on the other, side, I'm making an opposite, error. Well, then if you are an observer at the outlet, you cannot tell the difference, and actually everything is cool. So what this demonstrates is that that random errors in this high resolution radar rainfall field can be effectively filtered out by the river network, because we have many hill slopes. The travel time, here has only, few zones, here for this basin, it's about, 7 days or so. So there are plenty of opportunities to filter out the random variation. So I do not need to worry that much about random errors. And this actually goes hand in hand with what I was just showing before about the resolution, because the resolution, decreased resolution, it's kind of, the same as not accounting for all the variability. But again, I don't have to, because some of it will be filtered out. Well, okay, so let's continue, here, and so this is another insight, and that is it goes like this. So we will be using here two different radar rainfall, product. So you can see, perhaps you are very familiar with the multi-radar, multi-sensor, rainfall, kind of the official, product for the whole country, comes from NSSL. It's all good. They have a big team of people working on this, and periodically they have new and improved, versions. And then here we have Iowa Flood Center products. So because we do have expertise in-house, we also do this, but only for Iowa. So two different products. Of course, the basic, data come from the same network of radars. I'm not. This is just an example, just screenshot. I'm not, saying anything, which one is better. So that's not the point of this demonstration. Okay, so then we take those two products and we will be applying them to the very same hydrologic, model. But before we do this, I wanted to introduce this performance, metric that we will be using actually throughout the rest of the presentation. Again, it's well known in hydrology. We call it KGE, and you can see the components, here. And so there is correlation of the two time series, one being the model output, one being observations. You have a bias, and you have also some measure of just variability, like the ratio of the variance of the signal and the the observations and the model. And so again, one is very good. It can go actually below 0, but anything positive, so 1.8, 0.5, that's not bad. That's good. Yeah. So keep that in mind. So okay. So after applying those two different rainfall products to the very same hydrologic model, then we can look at the KGE and plot them like this, so you can see what is what. And of course, when things are below the diagonal, well, that favors one product here, MRMS, and this is IFC. So each dot is an observation or a KGE calculated at a stream gauge. So at stream gauges, we have stream flow observations. So if you were to count these dots, so what is it, like 47 plus 89, close to 140 stream gauges that are used here in this, construction. So these are USGS stream gauges. So, little in favor of MRMS, but it's not, something that you can say like hands down. So then we spend a lot of time looking for something that is important for hydrology, that distinguishes these two products, and it was really hard to find, to put our hand on what is it. So then we said, okay, rather than looking at differences, let's look at similarities. So here we said, okay, let's just adjust one product so that in the mean it will be exactly the same as the other. Okay, so we call this equalization. And of course, one or the other could be the basis for this. So now look what happens. This happened. They are the same. So to us, this implies that that the most important aspect of this radar rainfall field is to get the volume right. And if the volume is the same, then the details that are part of these two different products are just less important. So you can still not tell which product is better, but or you can say that if the mean is the same, then they are pretty much the same. So one can then say, okay, let's take this further. So maybe you don't need all this radar rainfall details. So what about like uniform rainfall over the basin? Well, if you do this, then you get this. So now you get more scatter, so that means that the details are important. If you don't include certain details, you are going to pay a price in terms of your model performance. Okay, so this is kind of a demonstration, just comparing two different products, and here on the right you can see that when those two, uniform rainfall and MRMS, are compared, then the differences have these actually large features, either underestimation in blue or overestimation in large. So that means if you are missing those, then you will have to pay a price. But we already learned that if you are missing small details and you are wrong in terms of small details, no, there is no strong price to pay. So that's a hydrologic insight here. And so well, so then the topic that perhaps this group is most interested in. So again, I'll give you a hydrologic perspective here. So let's say this is a basin of interest. So I'm interested in what happens at that red point, the outlet of this basin. And now let's say that this is the true rainfall. True rainfall was over the basin, so one would expect some response here. And let's say that this was the forecast. Well, so it's like when you look at this, well, based on what I know, it's like, well, this is good. This is a pretty good, forecast. And so the shape is almost identical to the true, the magnitude just slightly, different. It is just that it's in a wrong, place, but not by much, maybe 20 miles. But from the point of view of forecasting at this red point, it's a terrible, forecast, right? Well, not only from that point of view, but also from that point of view. So now I have another, basin, here, and now I'm going to be telling all these, people that's like, watch out, so something serious is coming, to you. Well, and so both of these basins, so one was like maybe smaller than this one, but now I will shift my point down here. Well, so this is now a big basin. So the true rainfall and the forecasted rainfall are kind of on the different side of the basin. And actually, this is the same basin that I used for demonstration of this travel time. So you guess what? It doesn't matter. So for that point in Cedar Rapids, this is actually a pretty good, forecast, because the water will get there, on time, and you will not even, know that it came from a wrong forecast. So what is the lesson here? Well, first of all, it brings this question: what is the value of QPF for Streamflow forecasting? And already intuitively, based on what I was showing, you could say that it depends, right? Depends on what? Depends on the scale of the basin, right? So we have done a little bit more on that. So I will be showing you some analysis that we have done to address, this point. So first, just rainfall to rainfall. So QPF versus observed rainfall. Observed rainfall in here is MRMS. Well, so you've seen that, before. So again, the scale here, I'm just showing correlation to just, keep things, simple. So strongly, depends and systematically depends on the scale of the basin. So again, this is 12-hour lead time. And then if I go to a different product, GFS, kind of, the same, story. And of course, as the lead time increases, well, then the scale, not only that it still increases with scale, but overall it decreases to something not worth writing home about. So, all right, so then let's translate this to hydrology. So again, you have this collection of some 140 points where we can evaluate things in terms of this KGE. So again, forecasted stream flow versus versus observed stream flow. I'll let you absorb these points a little bit. You can see the legend. This MRMS QPE, so we keep it here, and of course I don't know the future MRMS QPE, but here in the simulation I can pretend that I do. So we just keep it. So one can think of that as the limit for the QPF, because even if we knew how to forecast rainfall better, we will never know, because we cannot observe it better than what MRMS provides. So you can see here. Well, the alternative is that if you don't trust your QPF, you can say, okay, well, the rainfall stops when my QPE stops, right? No more rain. And you will be only projecting the response from what already happened on the ground, right? So you can see not that great, but but again, there is still some skill in that. And then the gray points are the forecast. So clearly the forecast skill increases as the scale increases. So, but for the small scale, not so great. And this is then the lead time, 18 hours, 24, and so on. So kind of a messy, picture, here you have to look closely to see things, emerging. So like, for example, here on the lower right, we can see that the blue kind of sinks to the bottom. Well, because the blue says no rain, and so there's like no rain for a long time. But what if there was rain? So MRMS says there was rain, and so there's just a different level of skill. So that's one insight. And of course, it's messy because we already have uncertainty that I acknowledged in the hydrologic model as well as in the QPE. So this is just a different kind of demonstration here. So just some few examples here. So I have 18 hours of QPF from HRRR. So you all know what this is, this high resolution QPF, but only for 18 hours. And then so again, the red dot, the red markers, here. So this is MRMS only, but again, so MRMS product into the future doesn't depend on any particular lead time. So it varies, slightly from location to location and from scale to scale, but it's pretty good. So 0.7, 0.6. So this is pretty good performance from the model. So the rest of the uncertainty is from combined QPE and the model, the hydrologic model. And then you see this other things. So for this very large scale, I go to the right, whether you say no rain, or when you use your forecasting system, it really doesn't matter, again, up to some point. Why is that? Well, because, and this is, I don't have any like other demonstration of this, but I just hope that you will agree. So the water is already in the rivers, and now the additional amount of water that that comes with a storm is a fraction of what is already in the river. So whether you say no more rain or a little bit more rain, it just doesn't matter, right? It matters for small scales, but not for large scales. So we can see it here. So the good news is that making this assumption of no more rain, which is only for people who are like really afraid of forecasting rainfall, the skill quickly goes down, right? And then the rest you can see for yourself. So for HRRR, well, again, it's like really hard to tell, because I should have a different demo with even a smaller scale. So 640 square kilometers, that's not a large basin, but I could have gone to 100 square kilometers, or maybe even smaller. So it is for those basins. If we don't have those problems that were in my schematics, then we could have a very nice story. So well, so this is now another synthesis of the results, and here presenting them in some with some attempt to normalize things, because so far I was talking about basin size, but that may not be, so it's kind of hard to compare different sizes, right? So but here it's like some dimensionless time, where the lead time is divided by some travel time, so of the basin. So then we have these ratios here, and so then a more clear trend appears. Again, this confirmation that no more rain, that's not the best strategy. Again, MRMS in red, that's kind of your limit, and then everything else with the existing QPF. And then the same going to wider range of these times, a kind of similar picture here. So this case is, let me see, yeah, so this case is without data assimilation, and this is the same with data assimilation. So again, and the data that are being assimilated here are for Streamflow. So but that assimilation only works in the downstream direction. So it's much more difficult to do it in the upstream direction. So well, so I could stop, here, but I do have a pet peeve, and so that I want to share with you. So it's kind of the opposite of, pet peeve. It is about persistence. Okay, so persistence in Streamflow in time. So look at this. So I have now, again, that KGE lead time all the way to, what is it, 3 days. So look at this. For, again, big basins, I can be just using persistence, and, you have to respect me, so, and certainly like 1 hour ahead, one day ahead, right? Okay, but this in time. So I can only do this where I have, gauges. But this is now another construction. This is now persistence in space. So, I'm standing here on a bridge, and I know how much flow there is, and somebody comes next to me and says, like, so what do you think? How much water is flowing, 20 miles downstream? And, I don't want to say that I don't know. So I just say, well, the same as here. Okay, and there is your persistence, scheme. And look at that. So here is again that KGE, but now, of course, the distance between the gauges matters, but hydrologically, it's not actually the river distance, it's how much landscape you drain. So if I'm draining 70%, right, the gauge when I observe versus the gauge where I have interest. So if I monitor 70%, I'm at 0.6 kGE. Well, that's respectable, and so on. So this just explains that monitoring area, ratio. So yellow is a small portion, but things increase as you get, closer. So I'll skip this because you can see the construction, now, and with the construction, I can make this. So this is a river network, and I have some gauges. Actually, those are locations for USGS, gauges, and then short distance upstream, and then a longer distance downstream. I can use persistence, and this is a map of that KGE. So again, for small streams, yeah, I have no skill. For these bigger rivers, yeah, I'm good, so that's why people can say like a month, ahead, what will happen in New Orleans if they know what's happening on the Mississippi here in Iowa, right? So that water will not disappear. Now, if I add these Iowa Flood Center bridge sensors, well, then I further enhance my predictability, in space. So I call this, pet peeve, because it's like, as a modeler, like I'm upset, how well this persistence, is doing, so, and of course, I know that other modelers are, upset, too, seeing, this. So especially those who are doing artificial intelligence. So, well, so I will stop, here with this picture of beautiful Iowa. So thank you very much, and I hope you enjoyed this.
Thank you, Professor. We have a couple minutes for questions. So if anyone has a question, you can go ahead and raise your hand, or you can just type your question in the chat and I will unmute you.
So I have a question. So it looks like the GPM I-merge precipitation product outperforms the other NOAA product for your hydrological modeling and forecast. So can you give me some comment about the end? Why the GPM I-merge product seems better?
I did not use that product in this demonstration here. I just mentioned that in my study of the rainfall resolution, there is still decent performance when the resolution is on the order of that of satellite-based products. That's all I did.
Okay, got you.
Jackson raised his hand up first. You can go ahead and ask it, Jackson.
Okay, thank you. Yeah, okay. I'm rather intrigued by your result earlier on when you talked about the seemingly lack of importance of random error. So one of the things that we are, like in terms of retrievals, that we are sort of focusing on is trying to predict uncertainty. So instead of giving you a single number, 2 millimeters per hour in this grid box, it will be a PDF, a spread of information. So, and this spread is meant to capture random information. So does this mean that at least for your purpose of modeling stream flow at a certain scale, this sort of information is not really that important? Is there something you can do if I were to provide you with this uncertainty information?
Well, so I was saying that it is important to have the volume right. But also you and I, we both know that working with actual, data, especially in this business of remote sensing of rainfall, it is difficult to distinguish systematic from random errors. So now I was not necessarily implying that it doesn't matter at all. It matters less and less as the scale of the basin increases. If your interest is in, say, flash flood, scale, then of course it doesn't, matter, right? Especially if those random errors have high variance, like they would if for that case of my schematic illustration with those basins and mist, forecast, right? Right, so that was like way off, and so the consequences at the small scales would be severe.
Okay, right. Thank you.
You're welcome.
Thank you, BLI. He's been waiting for a second, or Blee. You can ask your question.
Hi, yes. Hi, this is Bailing. Very nice presentation. I have a question. So in recent years, there have been many studies showing that the machine learning models, especially the long short-term memory networks, have can outperform the traditional either the rainfall, runoff model or the land surface models in terms of predicting stream flow. I wonder if you have any thought about that. I mean, are you interested in the machine learning models or any comments?
So yes, certainly. So just to say that I'm not totally ignorant, here my best cited, paper from some 30 years ago on neural networks, was on that, so, but anyway, that aside, okay, so I wrote a paper recently telling AI, people that before they kind of brag about the performance of their AI-based, models, they have to provide some reference. And so the idea is like this. So I demonstrated this performance from persistence. So if this is just to set an example, if from persistence, I can get KGE of 0.8, then the room for improvement with any model, AI or not, is only from 0.8 to 1. Okay, so this is the territory to fight about. If with persistence, I can only achieve 0.1, then there is much more room for improvement. So now, so I proposed in the paper, it's in Journal of Hydrology, that modelers should do persistence, well, in space and time as a reference. I'm not advocating that as a forecasting method, but as a reference, so that they can demonstrate the actual value of their modeling. Because this is, if anything, this is the problem that I see with many of these papers, that it's very difficult to then compare one paper to another, because there's another problem in hydrology, so one person does a study here and another person does a study there, and you can look at these metrics, but without the strong specific context, they don't mean much. So my proposal was do persistence and use it as a reference.
Thank you.
Do we have any other questions? Oh, I see Ralph. Ralph, you can go ahead and ask your question now too.
Okay, yeah, Vitek, this is just maybe not directly related to your talk, but I pick your brain on this one. So have you seen any evidence from your data of more extreme events? That's one of the climate change scenarios. I mean, I know in our area here in Maryland, we seem to be having more of these where there's 5 inches of rain, flood, and then you drive 2 miles and the road's dry. Do you see any evidence of that, or is your group looking into things like that?
Yes, so my colleagues, do, and sometimes I participate, too. So Gabriele Villarini is the guy. I would strongly recommend that you invite, him, and he will tell you, all about this. But yes, so it's about properties of extreme rainfall, properties of, floods, attribution, studies when you see things, changing. So yes, we definitely are involved in studies like that.
Okay, great, thanks.
Can I ask a question also? Hi, Vitek.
Yes, hi, Effie.
So this is great to evaluate the I'm going to say the capturing of the precipitation space-time variability in the context of stream flow at the end of a basin as a function of scale. But in the example that you had, well, if precipitation was here or there, does not really matter, because they will reach that point. But if there was community A flooded or community B flooded completely and inundated, or it was a bridge or extreme rainfall or something that was very localized catastrophic damage, this is a different perspective that I would care to capture precipitation if it happens here or there, and not put them in the perspective that it's okay because they're equal distance to the travel time distance to the outlet, and it will arrive there anyway.
No, so my argument was going across scales. So if you are at a small scale and you are off, well, then there are consequences. Only as the scale increases, then there are these mitigating factors, if you will, and that is the workings of the topology of the river network to filter out certain types of errors. So
Yeah. Thanks.
Do we have any other questions before we wrap up today? Okay, well, thank you everyone for coming to our seminar today, and thank you so much, Vitek, for speaking to us. This was a great talk. It's always nice to have you know, some Marylanders come in. Yeah, so I hope to see everyone here next week as we continue our seminar series. Thank you.
Thank you all. Thank you very much. Thank you.